Please, everyone, welcome the next group. I'll introduce them. Dr. Burkhard Ringlein and Dr. Jamie Yang of IBM Research are two of the leads for the Triton kernel team at IBM Research. And Rishi Astra is a third-year honors CS undergraduate at the University of Texas at Austin. He specializes in low-level GPU optimizations and CUDA. His recent projects include advanced LLM quantization and optimized fused Mamba 2 LLM kernels. The title of their presentation today is Triton for vLLM. Please welcome our next speakers.
Yeah, thank you, Jason, for the kind introduction, and thank you to Stephen for organizing this meetup. It's a cool event. I just would like to add for this introduction, I'm from IBM Research in Zurich, and I flew in for this workshop and other workshops yesterday, so my body is still at 2 a.m. in the morning right now. So I hope you bear with me if I'm a little bit slower than usual this time. Yeah, we present, after introducing Triton and introducing vLLM, I guess the next logical step in this presentation is to go deeper on Triton for vLLM. We present in this presentation a lot of work from wonderful colleagues in IBM Research Yorktown and Zurich. We just had all the names here, so shout out to them. And yeah, let's get started. I guess Triton for vLLM is a big topic, and we could easily produce talks for a full day on it. And we thought, okay, for this meetup, it's a little bit hands-on. What do we want to do? And we decided on this agenda. We will introduce to you the backend for vLLM we did for Triton in IBM Research. Then we thought, well, this meetup is also, most of you are engineers, I think, so maybe you are interested in how we did it and how we daily work and how you could achieve something like that. So we do a little bit behind the scenes. And then in hopefully 8 minutes, I will hand over to Jamie to talk to you about a new model architecture called Mamba. And then a few minutes later, Rishi will talk to you about kernel fusion and going really low into how Triton works. Yeah, I can skip this slide because Luca presented what vLLM is, so you all know. I will just tell you what vLLM backend is, and because I personally feel backend is a little bit overloaded term. Every framework has now a front end and a backend and something in between. So the backend for vLLM and what this talk in the next 5-6 minutes is about is the attention layer in vLLM. vLLM is a big piece of software. It's a de facto LLM engine, and it has a lot of scheduling, so that's a big box there. It has modeling code for all the models. It has runtime and execution code. And it has all the model layers. And the performance of LLMs sit on the attention layer. So that's why vLLM decided to wrap this in extra abstraction that is called the backend. And this backend then handles the execution of the attention for all phases, like the prefill phase, the decoding phase, and the prefix caching as well. If you are not into LLMs, typically LLMs have two distinct execution phases. One is a prefill phase where if you have a system, if you have prompt to the LLM, like write a Shakespeare poem, then this prompt needs to be parsed, like the attention computed for this complete prompt, and then the model starts to answer. The first one is called prefill, the other one is then called decoding. Usually prefill is a compute bound, decoding is memory bound, usually depending on the platform. And that's all wrapped in this attention backend. And until a few weeks ago, there was no Triton backend for vLLM, and that's why we did that. And yeah, we in IBM Research did a production-ready backend for vLLM in Triton. It's actually merged in vLLM in the meantime. Your eyes, I guess, goes immediately to the plot on the right-hand side. This is the plot for MI300, and we were able, with our backend, to get a speed up of 5x with the first 2 PRs, and now we have more PRs lined up, and we'll go to that in a minute. Our backend is also implemented as a plugin for v0, if you use the old version of vLLM. It contains multiple kernels and also is shipped with the Autotuning. So you will learn in a few minutes that you need Autotuning for Triton in order to be performant, portable across platforms. And we've taken care of that, so we ship the Autotuning configurations for the kernels we use in this backend, especially the flash attention prefill code. This backend also includes all the Microbenchmarking debugging environment that's necessary, and you can find it on GitHub in this beautiful URL. I guess we do questions in the end, or now? How do we do it?
Yeah. We can hold questions to the end.
Maybe if that's okay.
Remember it, yeah.
Great, so I need also to remember what I need to talk, so and it's 3 a.m. Yeah, so we had 5x in the beginning for this 5x throughput improvement in the beginning, but that was a nice start, but we didn't stop there. After improving the kernels, we looked at the complete stack. And if you work with Triton, you notice pretty quickly that Triton has some significant launch overhead, especially for small kernels. What I mean by that is shown here in this PyTorch trace. So if you say in Python now execute the kernel, all of this happens until the kernel actually gets executed on the GPU. And that is 150 microseconds or 200 microseconds, depending a little bit on the kernel. That is not the compile time. So I hope you don't, it's of course confusing, but that's not the compile time. So that's orthogonal to what Steve presented. That is just the time that Triton needs to check, do I need to recompile this kernel? Because Triton is a just-in-time compiler, so it wants to make sure that the kernel that executes on the GPU is the right version. So it hashes the complete source code, it hashes all the arguments, it checks if the constant in the argument is still the same as the constant in the binary, so that takes a lot of time. And that's why Triton has a high launch overhead. There are usually two workarounds for this. One is to use CUDA or HIP graphs, and that's what most of people do. Then you don't have this launch overhead, because then the CUDA or HIP driver takes care of launching the kernel, and all of this launch overhead is skipped. But that also means that the arguments to the kernel freezes. So for a CUDA graph, if you have a pointer to a tensor, then you have to use the same pointer every time. And that creates some trade-off, because then you need to reserve memory in the GPU, and then you have memory friction. So for vLLM, they decided it's not really usable anymore. So for the attention layer in vLLM, there is not CUDA graphs. So we need to find another solution, and we need to cut through this launch overhead. And that's why we had caches already mentioned today a couple of times. We created another cache, because for application-specific circuits, application-specific circuits was my old PhD topic. For application-specific applications here, scenarios, you can actually skip a lot of these checks, because you know this number of heads, for example, within an LLM usually doesn't change from layer to layer. It's always the same number of heads, and so on. So you can cut a lot of these checks and just then assume, okay, I update this argument, because in vLLM only this argument changes for one execution to the next, and I reuse the rest, because I know this for this specific application use case. And yeah, that gives sometimes interesting speed up. So also here I put some plots on the right hand side for not Llama models, but now Mistral models. And on an H100, our backend is now actually more performant than Flash Attention 3, so CUDA native code on H100. And on MI300, we got some speed up. And just notice that we have different y-axis here. So that is another PR to vLLM. Then another thing we could do is to improve the parallelization of the attention kernel, to also parallelize the sequence itself, not only parallelize in the batch domain and in the head number of heads, so that is executed in parallel. You could also split up one request and calculate it in parallel. And I put that pays off for very long requests. So for short requests, it doesn't really add something, but for long output tokens, so if you create a long Shakespeare poem, then it really pays off. And some people wonder where the red line in this diagram is. So that is a Flash Attention 3 on H100 again, but actually the red line is below the green line here, because also here we are totally the same performance. And this does not include the optimization of the chit cache. So if we combine that in the next weeks, we hope we also are ahead of Flash Attention 3 for very long contexts. So that is what we did in the past, actually 2 months or so. And maybe some engineers among you wonder how we did that. So just briefly, we need an extensive suite of microbenchmarks with realistic workloads. And maybe if I sell microbenchmark, you think about, well, that's for the guys that are doing the tutorials or for undergraduate students doing their homework. But no, we realized this LLM stack is quite complex. And if you have some end-to-end performance and you cannot explain how your end-to-end performance add up to the kernel performance, then you need microbenchmarks that has the same workloads, the same parameters like end-to-end. And I just point to you some of the plots I then study. That is just for one model, how to see, okay, how the kernel behaves in different scenarios compared to our CUDA baseline. Then also this microbenchmark makes it much easier to debug just the kernel, because if we have a big stack like vLLM and we want to debug new kernel, yeah, then good luck setting this up. But nevertheless, you also need, of course, holistic and quick end-to-end tests. So just briefly, before I hand over to Jamie, one comment on autotuning. I mentioned autotuning is important. We have a lot of research that shows that you need autotuning on Triton to be performant, to have performance portability, so to have the best performance on each platform. And that is shown in this plot. So for example, also that it's now not our backend, that is the flash attention kernel also used in our backend on A100 MI250, and there you see, okay, we are a little bit behind the ROCm or CUDA baseline, but if you tune the Triton kernel manually, then depending on the workload, you have a variance of 100x sometimes on the performance if you do not use the autotuner. And also I highlighted here, if you use the autotuner, you don't have any you don't need to change any line of code to run on a different GPU platform or even a different vendor. The reason for that is I tried to explain in this figure. That is a very complex figure. I just want to show you a little bit why the autotuner is so important for Triton. I plotted here 450 different configurations for just one setup. So if you have flash attention for Llama 3, 8 billion with 1,000 input tokens, then the autotuner can go, so that's a very tiny workload. But even there, the autotuner can go through 450 different configurations. And I plotted here the runtime in purple, and you see it different by 100x between best and worst. Then I plotted the size of the binary in green on the right-hand side, and you see also the size of the binary changes a lot depending on how much you use software pipelining, how much the Triton compiler decides to use loop unrolling, and so on. Also, the number of vector instructions and so on change, and there is no really prediction that the binary with the best, deepest software pipelining doesn't necessarily have the best performance. Also, the binary with the shortest software pipeline doesn't have the best performance. Somewhere in between is the best performance. And if that was now a little bit quick, I can understand you. That was just a little bit of advertisement of upcoming paper that will be posted in the next days, hopefully, where we say really why Triton autotuning can solve the performance portability for GPU. Then you don't want to do autotuning while the inference server is running, because to get this data takes 12 hours of compute, and we speak about speed up vLLM startup time for 30 seconds, so then you don't want to add 12 hours of latency there. So that's why you need to do autotuning ahead of time. And that's what our framework Triton Deja Vu does. That says, well, the autotuner then remembers, I did that some time ago, and reuses that knowledge, basically. That's where this French word Deja Vu comes from. And also that is open source, and you can use it, and actually a lot of people do in the meantime. So now I'm 2 minutes late, sorry for that, but I don't need that. Okay.
Okay, so thanks to Burkhard. I'm Jamie Yang, and I'm also from IBM Research. So just to maybe briefly summarize what Burkhard presented, it's about how we did all of these changes to either enhance how we deploy transformer-based LLMs on vLLM, right? So in the next part, we're gonna briefly mention this kind of new emerging architecture, which is called Mamba. And the reason that Mamba is interesting for us is that it's a new architecture that kind of solves a very important bottleneck in transformer-based models. Because in transformer-based models, in the attention mechanism, you need to create KV cache during autoregressive phase. And the KV cache size actually grows when you, when you generate more tokens. And because of that, you can actually imagine the attention kernel is gonna become slower and slower as you generate more tokens. But the Mamba architecture kind of proposed a new way to kind of solve that problem by using a state space model And they, with a change to how state space model is represented, they basically let some of the states also evolve with time. But by doing that, they can keep the cache, which is the cache for the states, a constant size. So that's in comparison to the KV cache in transformers, which grows as you generate more tokens. But in Mamba, the state cache will remain the same size. So in that way, it kind of removes the memory bottleneck, because you can, compared to transformers, you can have a kind of a moderate size cache, and that doesn't grow when you generate more tokens. And there has been 2 iterations on the Mamba architecture. In the first paper that was published by Albert Gu and Triton, they have this first iteration that theoretically it works well, and they actually also demonstrated that a pure Mamba model can model language, right? It can do language tasks pretty well. But the problem is that when it's implemented on modern GPU, it doesn't perform as well as transformers, because it doesn't utilize the advantage or the strong suit of the GPUs, which is to do a lot of matrix multiplications as fast as possible. So in the second iteration, they kind of tuned the model a little bit by introducing some more restrictions. So that kind of limits the expressiveness of the model, but at the same time, it enables it to be represented with matrix multiplications. I think it was a few months ago, IBM published a model called Mamba 9 billion. So this model is a hybrid model that combines or interleaves the Mamba 2 layers and the transformer layers. So there are in total 29 Mamba 2 layers and 3 transformer layers. And we published a blog about that, which we showed some performance numbers in it. And we can show that for a large batch size and long context, comparing to Llama 3 8 billion, which is kind of similar in sizes, the Mamba model can have higher throughput and lower latency, right, for large contexts. So one caveat there is that even though it works well on large contexts, some people notice that when they deploy it with vLLM, it doesn't really perform that well for a benchmark that the community, the open source community, likes to use, which is a benchmark that starts vLLM in the server mode, and there's a client script that's going to generate a lot of requests and send it to the server. But so we look at that benchmark script, and we notice that, oh, it's actually generating a lot of short prompts, right? Short prompts, and a lot of them in a short amount of time. And so one thing, why is that relevant to to Triton, is because in the current vLLM implementation, it heavily uses Triton kernels, and there are actually 6 kernels for the prefill phase and 1 kernel for decode phase. And so we did some investigation in why it doesn't do well for that specific test case. And we found that there are actually 2 problems with how the kernels are working right now. So one is that on the kind of the vLLM system level side, the implementation contains a lot of GPU and CPU synchronizations. And because you need to wait for some synchronizations to complete before you can launch new kernels. So that's actually slowing down and causing lower throughput for the short prompts. And the other problem that we notice is that So in the current implementation, the Mamba kernel in prefill, it can deal with a mixed input batch, meaning that the batch actually contains both prefill requests and decode requests. But whenever this scenario happens, even though the functionality is correct, the kernel doesn't perform well when you have a mixed type of a batch. So what we did there is that we submitted a few PRs to split the batch so that we basically split the prefill and decode requests so that they can be routed to specialized kernels, and these are still Triton kernels. So by implementing these changes, we are actually observing a 6x speed up for this benchmark. All right, so next we'll have Rishi to talk about kernel fusion.
Yeah, so I'll first give a bit of motivation on kernel fusion, and then we'll go back to Mamba 2 and fusing kernels there. So kernel fusion is useful when an operation depends on the results of a preceding operation. So if you have like one kernel and a kernel before it, if the kernel before writes some results to global memory, like those separate chips on a GPU, on a graphics card, if the second kernel then reads those same results as its input, you're kind of doing like this extra store and then load that it would be better if we could just do all that in cache and not have the extra cost. So two applications I'll discuss. One of them is potential methods for fusing Mamba 2 kernels. It's still an in-progress thing. And another one is a fused dequantization attention kernel. So as you saw previously, the original Mamba 2 kernels are in Triton, and they have multiple different Triton kernels for prefill and training. And our goal is to find opportunities for data reuse to fuse some of those kernels. So we're looking at two different methods. So one method is you kind of put all the code from the first kernel, and then a global barrier, and then all the code from the second kernel. So all of that in one new kernel. And now that might allow normally between kernels, the GPU driver might have to wipe some of the caches. So you can avoid wiping those caches. But a better method that we also are trying is we could have both the code for the first kernel and the code for the second kernel running at the same time. And that way, as we're generating output, we can start using that in the second kernel before the caches get full of data and start spilling to global memory. So we have some preliminary results. We can see that separately, the two original kernels read 1.4 gigabytes from VRAM. And they had a certain L2 hit rate, and that's the baseline we were using. Then if we use that global barrier between the two kernels' code and the fused kernel, it actually didn't really give any benefit. We actually got a slowdown, and it's still reading the same amount of data. However, when we finally made both steps run it concurrently, step one would just make some results, put it in L2 cache, then step two could read it from L2 cache. And they could synchronize so that we don't have too much data piling up between them. So then we actually got a pretty good speed up, and we can also see that the VRAM reads and the L2 hit rate are, so the VRAM reads are a lot lower because the L2 hit rate is much higher. So then another application of kernel fusion was a dequantization attention fused kernel. So we were working, this was last summer at my IBM internship, we were working on quantizing Llama. And one important part was the KV cache was quantized. But in order to use those keys and values in attention, we needed them to be dequantized. The attention itself was not using quantized values. So if we dequantize those values in maybe like just plain PyTorch or in a separate kernel, we're kind of, again, doing that thing where you store results, like, so you read the quantized values, you store the dequantized values, and then your attention kernel just reads those dequantized values again. So by fusing the dequantization with attention, we could reduce that from like read, store, read to just one read. And so we made this kernel based off of the OpenAI AMD Flash Attention Triton kernel. So thank you, AMD. And the code changes were relatively small. So basically where this is showing where it loads the values, you can see the original line not in bold. And for both keys and values, we just had to add a little extra logic to just do the dequantization. So because of Triton, we actually had, it was relatively simple to fuse those kernels.
All right, so to conclude, some of the points about Triton has already been talked about in previous talks, so I'll not mention them again. So I'm gonna talk about our future work. So on the vLLM Triton side, we're gonna keep focusing on attention kernel, including the 3D kernel that Burkhard mentioned. And a huge part of our contribution is on auto-tuning. And we're gonna try to auto-tune that and cover a wider range of things, and including potentially new hardware features like warp specialization and how that interacts with the auto-tuner. And we're also gonna expand our work to cover a lot of the AMD GPUs as well. And on the kernel side, we are looking into writing new kernels for emerging machine learning mechanisms, including Mamba we've already mentioned, and the fusion of those kernels, and multi-layer attention that is used in DeepSeek, and the group gem and MOE. And MOE has become pretty important, and as you know, Llama 4 uses MOE as well now. And also with the new upcoming hardware, there's always some new hardware features that may need us to evolve the algorithms that are used by existing kernels. Yeah, so I want to briefly mention that there's going to be a vLLM meetup that is hosted by Red Hat and IBM at New York. So if you're interested, please sign up for that, and please come talk to us. And we also have Sara and Krish. Maybe stand up a little. All right. Okay. I guess we can take questions now. So
okay. So my first question is really not that important, but you didn't really define what auto-tuning was, and I just wanted to know. But I actually have a much more interesting question about Mamba. Okay, so it just seems that auto-tuning is basically link time optimization on steroids, and I'm done, right?
Okay, so the question was what auto-tuning means in that context, and
well, you didn't define it, so.
Yes, that's right. I somehow assumed it's no. As in, Triton has. You can have constants in Triton like block sizes or how many warps you want to use, how many waves and so on. And these are arguments for the compiler. So the compiler thinks that as constant. And for different workloads, different block sizes or different optimizations make sense. And that's why you have the autotuner in front of the compiler to try out different versions for a specific use case.
Hyperparameter optimization for compiling.
Yeah, so for this you can take it as hyperparameter optimization, yes.
So my question about Mamba 2 is really, Mamba's big innovation was that it actually talked to the A100 hardware, exploited an SRAM resource that is unique to the A100 and of course the hoppers that follow it on. And so that's where they maintain their state space model, as I understand it. And so you don't seem to talk about that at all. You did talk about important bandwidth management. I mean, that your fusion is a huge advantage to be able to not do that management. But the big win for the state space model was actually using the SRAM, which was a hardware specific feature. One of the things that people talk about with Triton is that it's hardware specific. And so you're using a model that's claim to fame is what Triton did, was it used the hardware very specifically to manage that state.
Right.
So
Well,
confused by
I think you're referring to flash attention, though. I might be wrong. So Triton actually has a first paper on flash attention, right, where he exploited the idea of keeping the attention's weight matrix inside of the SRAM, right? So that's kind of I think that was the first paper that he brought forth this idea. And for Mamba, it's more about how do you overcome the limitation of needing to grow the KV cache as you have to in transformer blocks. And in Mamba, they are keeping a constant size cache, right? That's in the V1 paper. But in V1 paper, it's not exploiting the matrix multiplication hardware. So in the V2 paper, they tuned the model so that it can start using more of the matrix transform computations. But also, yes, he also, in the Mamba kernel, he was also keeping a lot of that in SRAM as well.
So is that something that's a resource that's exposed to the Triton model, or is that he knew special secret escape codes to go down in?
No. So yeah. So in Triton, you create tensors, right? You don't actually know whether they're going to be register or SRAM, but I think when you control the tiles that you allocate by changing the size of them, right, the compiler will do its best to keep them all in SRAM or registers, unless it has to spell. But I think for when you use too much, it's not actually going to compile, right? Yeah, it's actually going to generate compile errors.
Okay. Thank you.
All right. There's another question. Yeah.
Can I just pass the microphone over just so I get...
So at one point you mentioned there are a lot of data centers between CPU and GPU, right? So do you have any estimation of how much percentage of compute goes to CPU versus GPU in any of your experiments?
Yes, at some point we do have those data, but it was not organized and presented. So yes, I mean, so whenever you need to synchronize, right? For example, if you need to read a value from GPU tensor back to CPU tensor and you use it in an if-else statement, in that case, you're gonna have to wait until the if-else happens, right? And before you can launch any other GPU kernels. But I don't think there's like a typical ratio of the overhead. It really depends on whether when you write the PyTorch code, are you very aware that, oh, I should try to keep everything on device and I need to express whatever conditional thing that I need to do as much as possible using torch operations. Go ahead.
For Deja Vu, so like I would like to know if there is any way to verify the integrity of the cache like that Deja Vu generates.
Difficult here. How does this work? Okay, I hope this works. Yeah.
The question?
Okay. Now, okay, so for the recording, the question was how can we trust the caches Deja Vu generates? And it's a very complicated question, and I spent a lot of time trying to determine which factors exactly contribute to if I can trust a cache or not. And the factors include, if my memory doesn't fail me, it's of course the hash of the source code, it's the parameter list of the kernel, it's a parameter list of the Autotuner, it's a CUDA version, it's a Triton version, it's not the PyTorch version. It is the GPU, of course. I guess it was. I guess that was it, basically. And Triton Deja Vu checks that if all these conditions are met, and the cache has an index for that, and it indexes at the right place to use the right cache then. Actually, Triton just-in-time compiler has a similar checks to check if they can reuse a compiled binary or not. And these are more strict. So for the Autotuner, we learned you can be less strict on that, and you can reuse more what you did.
But like, what about the JSON itself? So you listed also, time in millisecond for each one, right?
Yeah.
And so like if an attacker, let's put like another number there, what can happen there? I mean, like, do you check somehow the integrity of the JSON?
Okay, so the question was if I check the integrity of the JSON. No, so I assume no one attacked the JSON. But it's a valid question. I didn't think about this attack vector. I just put it out, but maybe someone like you can protect us against this. But it's a valid question. Yeah, it could be some kind of DDoS attack in the end, right? You would degrade the performance of the model by that. Yes.
Actually, with Steven and our team, we are working on the cache, also like creating some signature for it, and also some checksum also. That can be something that we can use. Maybe we can.
Yeah, maybe synchronize on that offline would be very great.
Absolutely.
Okay, so we are good out of time, but I guess that's the spirit of this meetup. Any more questions? Or do you want to go to the food again? Okay, I guess we are. Thank you.
I'm so sorry. I'm going to take over for like 10 seconds. The meetup they mentioned, I just want to plug that again. We will also have people from Meta talking about the Torch compile integration, which I figure is very interesting to the people here for PyTorch. And if you don't want to be in New York in 1 week, because that's too early, we will also talk about it at the vLLM office hours. If you haven't heard of that, we run like a bi-weekly office hours where we just present vLLM topics. Any questions are welcome. Also like updates on the vLLM project. I know this is a PyTorch and a vLLM meetup today, but figured it might be interesting to some. So thank you so much.
So will the New York meeting be on YouTube or wherever for us to see also?
I don't think so. But the Torch compile topic will be like, we'll be doing an almost copy of the talk at the office hours, which is online.
Okay.